Hello, Mr. Boothman here. We're going to be talking about section 5.2 today. So let's go ahead and get started. So 5.2 is all about finishing the unit circle and then using the unit circle to evaluate the 6 trig functions. So we're going to start by finishing up the unit circle. And we're going to start by looking at special points on the unit circle. So first, here is the unit circle. Here's our center. And we know that this radius here is 1. If the radius is 1, then that means these points here on the axes are just 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Okay? Now, to get the rest of the points on the unit circle, like we have down here, we'll need to use, going all the way back to geometry, the special right triangles. So if you'll recall, these right triangles are 30, 60, 90. So we have 30 degrees here and 60 degrees up here. We could turn that on its side if we want the 30 degrees down in the corner. And we also have a 45, 45, 90 triangle. Just like that. And also from geometry, we have ratios of the sides of the special right triangles. So I don't blame you if you don't remember this. I certainly didn't until I looked it up, because it's been so long since we've used these. But these are the ratios of the sides of the special right triangles. Okay, so for a 30, 60, 90 triangle, whatever x is, the hypotenuse is 2x, the side across from 30 degrees is x, and then the side across from 60 degrees is x times the square root of 3. For a 45, 45, 90 triangle, the legs of the triangle across from 45 degrees are x, and then the hypotenuse is x times the square root of 2. So, why do we care? Well, we split up the unit circle into intervals of 30 degrees, 45 degrees, and 60 degrees. So if I take a look at this circle down here, if I take this 30-degree angle, remember we said this was 30 degrees, I can put my 30, 60, 90 triangle in there. Just like that. And I can use the ratios of the sides of the special right triangle to figure out what the lengths of the sides of this triangle inside the unit circle are. Okay? So, let's take a look at the 30, 60, 90. The radius of this 30, 60, 90 triangle in here, or the hypotenuse, is 1. That's because the radius of the unit circle anywhere in the unit circle is 1. So 1 equals 2x. So x equals 1/2. So we're matching the hypotenuse here with the radius here. All right. If x is 1/2, then that means this side is 1/2 and this side is 1/2 times the square root of 3. So we get these lengths of the sides of the 30, 60, 90 triangle. And from here we can say, looking at this point here, that this is our x value, right? If we want to put the unit circle inside the coordinate plane, this is our x value. Here I'm going to go ahead and erase this here. So we have the square root of 3 over 2, and then our y value up 1/2. So those are the coordinates of this point on the unit circle at 30 degrees, or pi over 6. And we can do the same thing with our other special right triangles. Here, if we want to get this out of the way here. Oops, didn't mean to do that. If we want to do the 60-degree triangle here, then again, the hypotenuse is 1 because the radius is 1. And this side is the square root of 3 over 2. We just flipped it on its side, our special right triangle, and then this side is 1/2. So the coordinates of this point end up being 1/2 times the square root of 3, or 1/2 and the square root of 3 over 2. So that gives us those points. And finally, we can take a look at the 45, 45, 90 triangle, right here, this was 45 degrees, so that means this is 45 degrees and this is a right angle. The hypotenuse is 1, and then if the hypotenuse is 1, then x is 1 over the square root of 2. And remember, we don't usually leave a square root in the denominator. We do what we call rationalizing the denominator. Multiply by, this is really 1. But when I multiply by the square root of 2 over 2, square root of 2 times the square root of 2 is 2. So it gets rid of the radical in the denominator. So each leg is the square root of 2 over 2, which means this point's coordinates are the square root of 2 over 2, square root of 2 over 2. Okay, so because we split up the unit circle into 30, 45, and 60 degree increments, we can use our special right triangles from geometry and the ratios of the sides of those triangles to get us the coordinates along the unit circle. So knowing this, we can fill in all of these points. So I'm going to start with angles. So this was 30 degrees. Here, I'll do degrees first. 30 degrees, 45 degrees, 60 degrees, so 0. 90, 120, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330, and 360, back at where we started. Okay, and I'll go ahead and fill in radians now. Let's do yellow here. So this is 0 radians, pi over 6, pi over 4, pi over 3, pi over 2. This is 2 pi thirds. This is 3 pi fourths. This is 5 pi over 6. This is pi. 7 pi over 6. 5 pi over 4. This is 4 pi thirds. 3 pi over 2. This is 5 pi thirds. This is 7 pi fourths. 11 pi over 6, and then back at 2 pi. So those are the radian measures along the unit circle. And we can get our points. So here we had from 30 degrees, square root of 2. Remember, we get these by putting the special right triangle inside the circle. So we have the square root of 3 over 2 and 1/2. And if we go on this was first coordinate, or the first quadrant. So if we go over here in the second quadrant, right here, that's going to have the same coordinates if I put the triangle over there, except that the x-coordinate is negative, because x is negative in this second quadrant. We're on the left side of the y-axis. So this will be negative square root of 3 over 2. And then I'm still going up 1/2. Okay, I can look in the third quadrant. That will be my 30-degree angle in here. Okay. And here, both x and y are negative. So that's going to be negative square root of 3 over 2, negative 1/2. And finally, I can look in the fourth quadrant. Here, x is positive, so square root of 3 over 2. And then y is negative, negative 1/2. Okay. Before I forget, I'm going to go ahead and fill in these points here that we did at the very start of this section. 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Okay. So we filled in the 30-degree angle points. Now we can fill in the coordinates for the 60-degree angles, the pi over 3. So here, this time I'm going over 1/2 and then up square root of 3 over 2. And just like I did with 30-degree angles, I'm going to look and see here x is negative, y is positive, so it's the same coordinates. I'm just changing my sign. Okay, that's there. Here in the third quadrant, both x and y are negative. Here in the fourth quadrant, that was the third quadrant. Here in the fourth quadrant, x is positive, y is negative. Okay. And finally, I'm going to look at the 45-degree angles, starting right here. Here we had, just like up here, square root of 2 over 2, square root of 2 over 2. So those are the coordinates here. And again, x is negative, y is positive. X and y are both negative, and x is positive, y is negative. So just like that, we get the coordinates of our points on the unit circle. So now, what can we do with this? What does this have to do with trig? We also need to go back to geometry for this. So we ask ourselves, I hope we remember SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, so sine of an angle. This is theta, this Greek letter here. It's how we talk about an angle. Sine of theta is opposite over hypotenuse. Cosine of theta is the adjacent side of the triangle over the hypotenuse of the triangle, and tangent of theta is the opposite side over the adjacent. So this is how the Greeks defined these functions. They're just ratios of the sides of a triangle. So if we want to look at a triangle here, if this is our theta, then this is the opposite side, this is the adjacent side, and this is the hypotenuse of the triangle. SOHCAHTOA, I learned this as some old hippie, sine equals opposite over hypotenuse, caught another hippie, cosine equals adjacent over hypotenuse, tripping on acid, tangent equals opposite over adjacent. I believe I used that in class, and some people seem to know that. Some people were quite amused, but that is how I learned originally when I took geometry. But however you remember is how you remember. So using these definitions, if we want to look at these special right triangles in a unit circle, I'll scroll back up here, if it lets me scroll. Suppose we're looking at this angle here. Let's call that theta. So sine of 45 degrees. So sine here is going to be the opposite side over the hypotenuse. Well, anywhere we are inside the unit circle, the radius is 1. The hypotenuse of a triangle we draw is 1. So hypotenuse we can kind of just ignore when we're looking at our definitions here. It's not letting me scroll very easily. Here, so this will be 1, this is 1. So sine is really just the opposite side, and for any triangle we draw in the circle, the opposite side is the y value. So that's why we can define the trig function sine to equal the y value. Cosine will be the same thing because the hypotenuse is 1. Cosine, the adjacent side, will be the x value. And then tangent is opposite over adjacent. The opposite side is the y value over the adjacent side is the x value here. And then cosecant is the reciprocal of sine. We put 1 over y. Secant is the reciprocal of cosine, 1 over x, and then cotangent is x over y instead of y over x, like tangent. So this is why we care about all of these points on the unit circle for these particular angles, because now, and I believe you're doing this on your own, and this on your own, those are the ones that are circled in your guided notes. Go ahead and do those on your own as independent practice. That helps us do things like evaluating the 6 trig functions. So let's look at t equals 5 pi over 4. I want the sine of 5 pi over 4. 5 pi over 4 on the unit circle puts me right here. So here is my point. Tangent is, or not tangent, cosine is x and sine is y, right? X, y, cosine of theta and sine of theta. So the sine of this angle is negative square root of 2 over 2. And then the cosine for this angle is going to be the same thing, negative square root of 2 over 2. The tangent is the y value over the x value. So in this case, x and y are the same, so anything over itself is 1. And then cosecant of 5 pi over 4. I need to flip this over, negative 2 over the square root of 2. We rationalize the denominator, and when we do that, we'll end up with negative square root of 2. Secant is going to be the same since cosine is the same as sine in this case. And then cotangent, 1, take the reciprocal of 1, that's 1. Okay? And here I do want to point out that you should never just write sine equals something. Okay? Sine, never do this. Sine is a function. It's something I'm doing. So I need to write what I am taking the sine of 5 pi over 4 in this case. Okay. So 0, if I look at the unit circle and look at where 0 is, 0 radians, or 0 degrees, although there's no degree sign here, so I will assume it is in radians. My point there is 1, 0. 1, 0, so the sine of 0, remember this is cosine of theta, sine of theta. So sine of 0 is 0. Cosine of 0 is 1. Tangent of 0 is y over x, 0 over 1, which is 0. The cosecant of 0, that's going to be 1 over 0, which we can't do, so this is undefined. Okay, secant of 0, this will be 1 over 1, which is 1. And then cotangent, we're going to run into the same problem, 1 over 0. And so this is also undefined. Okay. Take a look at pi. So my point at pi is negative 1, 0. So the sine of pi is 0. Cosine of pi is negative 1. Tangent of pi is 0 over negative 1. That's 0 again. The cosecant of pi, run into the same problem we ran into for t equals 0. So this will be undefined. The secant is negative 1. Reciprocal of negative 1 is negative 1. And then cotangent will also be undefined. Okay. And we'll go ahead and look at letter F. Negative 7 pi over 4. If we want to see where this is on the unit circle. Not sure why it won't let me scroll. All right, negative 7 pi over 4. We're going in the clockwise direction. 7 pi over 4, so 1, 2, 3, 4, 5, 6, 7. So that puts us here at this point, negative 7 pi over 4. So our point is the square root of 2 and the square root of 2. So the sine of negative 7 pi over 4 is the square root of 2 over 2. The cosine of negative 7 pi over 4 is the square root of 2 over 2. Tangent of negative 7 pi over 4 is 1, since anything over itself is 1. The cosecant of negative 7 pi over 4, I'll need to flip this 2 over the square root of 2, and when I rationalize the denominator, I will end up with the square root of 2. Cosine is the same as sine in this case, so the secant ends up being the same as the cosecant. And then cotangent of negative 7 pi over 4 is 1 again. Okay, so that's using the points pardon me, on the unit circle to give us a way to evaluate the trig functions, since we saw how sine is equal to y, cosine is equal to x, tangent is y over x. So let's fill in the blanks here. The blank of the sine and cosine function is the set of all real numbers. That is the domain. Remember, domain is what we can put into a function. So for the sine and cosine functions, I can plug in any function value that I want. I have no problem with negative numbers. I can plug in fractions. I can plug in square roots. I can plug in 0. So I can plug in any angle value and get back an answer. The blank of the sine and cosine function is the interval from negative 1 to 1. That's including negative 1 and 1. And that will be the range. The range is the possible y values, the outputs of my function. And so I see that if I look at the outputs, the coordinates on the unit circle, none of these numbers is greater than 1 or less than negative 1 for sine and cosine. So for sine and cosine, my range is between negative 1 and 1. Sine and cosine are what we call periodic functions. Periodic means it repeats regularly, right? Every 2 pi, I can go around the whole circle again and get back to the same point. So that's what we mean by periodic. The tide is periodic. It repeats regularly. So the period of the sine and cosine functions is 2 pi. They repeat every 2 pi, or 360 degrees if we're using degrees. So this is going to be especially important when we look at our next page here. What happens when the angle doesn't show up on the unit circle? Okay. So this is all nice. We just looked at how we can evaluate functions, or the functions for certain angles. But those angles were all one of our special points: 30 degrees, 60 degrees, 45 degrees, or if we continue adding one of those numbers. But what if I want to know a different angle on the unit circle? If I want to evaluate the trig functions for a different angle, not 30, 45, or 60 degrees, or one of their multiples. In that case, there are two things I can do. And we're going to look at the second thing in section 5.3. But for now, excuse me, this is the last thing we'll look at in this section. I'm going to try adding or subtracting 2 pi, or 360 degrees. Until I get an angle that's easier to use. Because, like we just said, sine and cosine are periodic. They repeat every 2 pi. So maybe I just have a really big or really small angle, a really negative angle. And so if I add or subtract 2 pi to that, I might be able to get an angle that I recognize on the unit circle, one of my coordinates that I can easily use. So, sorry, excuse me. You were doing A and F on your own. Okay, but we're going to go through the rest of them. So here I have the cosine of negative 7 pi over 2. Negative 7 pi over 2. Now, I don't see negative 7 pi over 2 on the unit circle. I could certainly try to figure out where that is going around the circle, but negative 7 pi over 2, it's going around quite a few times. We might feel more comfortable with an angle that we can see right away on the unit circle. So let's try adding 2 pi, right? Because these are going to be coterminal angles. Remember, coterminal angles from section 5.1. Coterminal angles, when I evaluate the trig functions, are the same, really, right? The sine of 0 degrees is the same as the sine of 360 degrees. I just go around the entire circle again, and I'm right back at this exact same point. So I can add or subtract 2 pi to any angle, and it's going to give me the same answer in the end. So negative 7 pi over 2, I'm going to add 2 pi. So for this, I need a common denominator. It's going to be negative 3 pi over 2. That's a little easier to work with if you want to figure out where the negative angle is, or I can just add 2 pi again if you like positive angles. I'm going to get pi over 2. So this is equal to the cosine of pi over 2. And pi over 2, my point is 0, 1, so cosine is 0. And that's it. That's all I need to do. So let's go through some more examples. 5 pi here. This, in this case, is a big angle, so I'm going to subtract 2 pi. 3 pi, I'm going to subtract 2 pi again. So this is really the sine of pi radians. And my point there is negative 1, 0. So there, the sign is 0. Okay? So I'm adding or subtracting 2 pi. It's going to give me the same answer as if I went around 5 pi radians and figured out where that is. 8 pi over 3. Subtract 2 pi. 2 pi in this case, when I get a common denominator, is going to be 6 pi over 3. So this ends up being 2 pi thirds. So the cosine of 8 pi over 3 equals the cosine of 2 pi thirds. And my point there is sorry, the negative 1/2 and the positive square root of 3 over 2. So cosine is the x value, so my answer is negative 1/2. Okay. Cosecant of negative 15 pi over 2. Negative 15 pi over 2, add 2 pi, which is really 4 pi over 2. So I get negative 11 pi over 2. And that's still a negative number, so I can add 2 pi again if I want. In fact, I can add 2 pi as many times as I want until I get an angle that I'm comfortable with. Pi over 2. So this is really the cosecant of pi over 2. Cosecant is the reciprocal of sine. So at pi over 2, the sine equals 1, and then the reciprocal of 1 is just 1. Seems like a lot of work, I know, for just a simple answer, but sometimes it's worth it. I think it is here. So 29 pi over 6. Subtract 2 pi, because that's a weird fraction and a big number. In this case, 2 pi equals 12 pi over 6. So this is 17 pi over 6. I'm going to subtract 2 pi again. 5 pi over 6. There's an angle I recognize. Cosecant of 29 pi over 6. Then that ends up being the same as the cosecant of 5 pi over 6. And my sine value there, since cosecant is the reciprocal of sine, I need to know the sine value. The sine value is 1/2. So when I take the reciprocal of that, the cosecant is 2. All right, one more problem. I know this was a long video, it's a long section, but this really sets the foundation for the next 3 units. Like, knowing the unit circle is so important. It's crucial for your success in trigonometry. So let's take a look at this last problem, negative 7 pi over 3. I'm going to add 2 pi, and in this case, when I get a common denominator, 2 pi is 6 pi over 3, which gives me negative pi over 3. I'm going to add 2 pi again because I like dealing with positive angles. So the secant of negative 7 pi over 3, that's the same as the secant of 5 pi over 3. And at 5 pi over 3, secant is the reciprocal of cosine, so I need to know the cosine value. At 5 pi over 3, cosine is equal to 1/2, so secant is 2. And that's it. All right. Hopefully I did not confuse you. I know I kind of went through this quickly, but we've already gone through this in class. So hopefully if you're watching this, it's because you were a little confused in class, but this helped clarify some things, or at least gave you the answers to these problems so you know if you're doing it correctly. Please bring your questions to me and Miss Parker. We are more than happy to help you. And I really do want you to have a really solid foundation starting right now in trig. And that all comes down to how well you know the unit circle. So we'll be taking our quiz on this soon. Please, I hate saying memorize things in math, but you do need to know the unit circle. It will make your life so much easier. So whether you're just so comfortable with it that you can figure out what the coordinates are at a certain point, or you're the kind of person who you're more successful just memorizing it and being able to use it, that's fine. However you choose to do it, just make sure you know it. Please come to me if you have questions, and I hope you have a great day. Thank you so much.